Okay, so we're gonna hop into homework 3, part B. And our question here is, oh, good, okay. Question here is the local Nusselt number for conductive heat transfer over a flat plate with laminar flow is equal to 0.332 times Reynolds number to the 1/2 power times our Prandtl number to the 1/3. If the objective is to maximize heat transfer over a rectangle flat plate of fixed area, explain why the flow should be oriented perpendicular to the longer edge. So, two things I started here with was I just rewrote our the rectangular plate with fixed area just to solid that or show that in so area does not change. And then here I have our boundary layer forming, which you can see in the red. And then here to here is our length, which we'll be using later. And then from here to here I just defined as x up here. So from our starting point where the fluid interacts with the plate to where our length is measured, I defined as x. So a Nusselt number is going to be our convective versus our conductive. So that will that's what we're trying to solve up here. Well, not necessarily solve, but find a value for to kind of explain why we would want to have our perpendicular orientation. So to get started, we're going to start plugging in units similar to part A. So let's start with our Reynolds number. So we'll have 0.332, which is a constant that was observed through experimentation, so we don't have to worry about that. But our Reynolds number is equal to rho Vx over viscosity, or mu. So we can plug that in for our Rex, well, and then we have to multiply, or sorry, the x is here, I already did it in my head, but the x is here to show that we're multiplying by x. So we're going to have rho Vx over mu sorry, to the 1/2, and then as hold on, I gotta check something and I'll be right back. Okay, so sorry, I just had to check the Prandtl stuff quick. So our Prandtl number is going to be equal to our momentum diffusivity. Oh my gosh, what am I doing? Over our thermal diffusivity. And so I'm just going to keep writing this over here. I'm just going to put P number. So we know our momentum diffusivity is going to be our mu over rho, so viscosity over density. And our thermal diffusivity that we use all the time for our problems is going to be K over Cp times rho, rho density. So when we rewrite that and cancel some things, we're going to cancel these two. Oops. Okay, cool. So we're going to cancel these two, and then we're going to have to flip the fraction over. So we're going to get mu, and then this bottom one's going to flip. So we're going to get mu times our Cp, or our heat, time over K. Cool, so now we can plug that in for our Prandtl number up here. So let me drag this down. Hopefully that got everything. Okay. So we can now add that. So multiplied by what we just solved, mu times Cp over k to the 1/3 power. Awesome. Okay, so now what we need to do is plug in our Nusselt number, which is going to be, I forgot to do that earlier. I got sidetracked and moved on, but it's going to be our h over k. And then since we're going to have to multiply that by our length, or not our length, our x here that I defined as x for the convective. So we can, let's just erase this and then I'll add that. So we're going to have hx over k. Okay, that looks good. So now what we're gonna do is we're gonna want to solve for h. So we're gonna have to multiply by k. So we'll multiply by k, and we'll multiply by 1 over x. Yeah, so that will leave us with our k on this side. And then, let's see, we can do some canceling. So we're going to have, or wait, I did that wrong. Okay, sorry, we're going to have h over here. I was so confused for a second. Okay, so we have 2 mu's here, but they're not going to cancel because they're at different exponents. And then we have our x and our k are going to cancel. So so here we have x to the 1/2, and we have x to the -1. So we're going to have x to the -1/2. I'm just going to write this up here. X to the -1/2. And we have k to the 1/3, or -1/3, and just k. So we're going to have k to the 2/3. And then everything can just be rewritten, basically. So we're going to have h is equal to 0.332. And then we got to make sure we cancel these. We'll add the k and the x at the end, but those k's and x's get canceled. So we're going to be left with rho v over mu to the 1/2 times mu cp. We don't need the denominator anymore because we got rid of k. To the 1/3, and then you got to add our new values up here. So we're going to have x to the -1/2 and k to the 2/3. Cool. Okay, so what this final equation is just telling us basically is that with this x right here, this raises a question of the to the -1/2. So you're going to want to get x as small as possible to minimize h being small, because you want h to be very large in order to maximize heat transfer. So if x is small, that means h is going to be large. So when x is small, h is going to be large, and vice versa. So in order to maximize this heat transfer, we're going to want a very small value. So what that's showing is the further and further we go out here on our x, the higher and higher sorry, the lower and lower our smaller our heat transfer is going to be. So say we have like an x here, our heat transfer is going to be maximized. So increasing surface area by the surface, like here, would greatly increase or maximize heat transfer. So hopefully that explains how flow should be oriented with this given number.